For example 2, a lot of this is review from what you did in a previous lesson that Mrs. Browning made a video for. The only part you really need to take notes for is the part where we verify that this function and its inverse are in inverse functions of one another. So the verification part is what you need to really take notes on. This example 2 is actually the same example that Mrs. Browning did with you in the first part of the 4.5 lessons. So there's really no need to jot down everything. All you really need to jot down is this equation, example 2, f of x equals 1/2 x squared minus 6. And remember what Mrs. Browning told you was that this function fails what we call the horizontal line test. So if a horizontal line is placed on this graph, it will cross two places at the same time. It's still a function. It's okay for a y-coordinate to have two x-coordinates assigned to it. It's just not a one-to-one function. So that means that when we reverse the x and y coordinates on this graph, we get this graph, which does not pass the vertical line test, and therefore it is not a function. So what we say is that, well, the inverse doesn't exist for this function right here because the original function was not one-to-one. So in order for a function to have an inverse, it must be one-to-one. This is actually two functions stuck together. The top half above the x-axis, or where the y-coordinates are positive, that's where y equals the square root of 2x plus 12. And the bottom half below the x-axis, or where the y-coordinates are negative, so y will equal the negative square root of 2x plus 12. And this was the equation that you derived with in your notes from the previous section that Mrs. Browning did. So restricting the domain of this function to where the x-coordinates can only be greater than or equal to 0 gives us half of the parabola, which passes the horizontal line test. So now it's a one-to-one function. And now we can find the inverse function. And Mrs. Browning did do that with you last in the video that you watched last time. And she mentioned that since the domain of this function is now x is greater than or equal to 0, then the range of the inverse function will be y is greater than or equal to 0. So the domain of f of x becomes the range of f inverse of x. And notice how that's just the top half of the parabola. The function f inverse equals the square root of 2x plus 12. So now let's do the part where we have to verify that these two functions are inverses of one another. And that's only true if x is greater than or equal to 0. So we have to do two function compositions. So we have to find out if f of f inverse of x is equal to x, and then we have to find out if f inverse of f of x is equal to x. Do the composition in the reverse order. So we're calling it f inverse of x instead of g of x this time. That's all. So let's do f of f inverse of x. That is f of the square root of 2x plus 12 because the inside function f inverse of x is the square root of 2x plus 12. That means that I look at the function f, and wherever there's an x, I replace it with this function, 2x plus the square root of 2x plus 12. And then I get this, 1/2 of the square root of 2x plus 12 in parentheses squared minus 6. And squaring undoes a square root, so that just leaves me with 1/2 of what's under the radical sign, 2x plus 12 minus 6. Distributing the 1/2, I end up with 1/2 of 2x is x, 1/2 of 12 is 6, and then don't forget the minus 6. And as you can see, the positive 6 and the negative 6 cancel, and we're left with x. So yes, f of f inverse of x does equal x. Now let's do the composition the other way around. Does f inverse of f of x equal x? And it is important that you write these steps down into your notes. If you need to stop the video to get that down, go ahead. Now let's write this part into our notes as well. So f inverse of f of x is going to be f inverse of 1/2 x squared minus 6 because that is the f of x function. That means I look at the f inverse function, and everywhere there's an x, and there it is, I'm going to replace it with everything that's here. So I'll replace it with 1/2 x squared minus 6 in parentheses after the 2. And that's what I have here. So again, under the radical sign, distribute the 2, and that will give me 2 times 1/2 x squared is just x squared. 2 times negative 6, that will be negative 12. And then don't forget the plus 12 at the end. And as you can see, the negative 12 and the positive 12 cancel each other out. And I'm left with the square root of x squared, which is x. So yes, f inverse of f of x equals x. So this is verified. That's how you verify that two functions are inverses of one another, by doing two function compositions. If you need to stop the video to get that all down in your notes, that's fine. Okay, for example 3, we're going to let f of x equal the cubed root of x plus 4. We're going to find the inverse function and verify that it is inverse. So go ahead and write this function down, and you can sketch a graph of the function. It goes through the point negative 4, 0, because when x is negative 4, the cubed root of 0 will be 0. So that's the 0 of the function. So this graph passes the horizontal line test, so it is a one-to-one function. That means that the inverse does exist. So I will go ahead and go through the process of finding the inverse function. The first step is to replace the f of x with y, and we'll have y equals the cubed root of x plus 4. And then the next step is to swap x and y. So we'll have x equals the cubed root of y plus 4. And then step 3, solve for y. And I'm going to start solving for y by undoing the cube root by cubing each side of the equation. So that will give us that x cubed is equal to just what's under the radical sign, y plus 4, because cubing undoes cubed root. Last step, subtract 4 from each side, and I get that x cubed minus 4 equals y is the inverse function. So this is our f inverse of x cubed minus 4. Please make sure that all of these steps are shown in your notes for finding the inverse function f inverse of x. So let's go on. This part you do not need to write into your notes right here. So I just want to verify that this function is the inverse by checking graphically. If you want to sketch a graph of the inverse function along with the graph that you wrote before of f of x, you can show that they are reflections of one another across the line y equals x. So checking graphically makes sense. I also like to check points on the graph to make sure I have the right inverse function. So for instance, 4, 2 is on this graph. That means that 2, 4 should be on this one. So I just plug in points, but let me warn you that a proof by using an example is not a proof. But just to show you that you can check to see that you have the right function. For instance, f of 4 would be the cube root of 4 plus 4, which is the cube root of 8, which is 2. And I purposely chose a number that would give me a perfect cube under here. So that means that f of 4 is 2. Well, if f of 4 is 2 and this is the right inverse function, then f inverse of 2 should give me 4. So let's find out. F inverse of 2 would be 2 cubed minus 4, which would be 8 minus 4, which is 4. And it does check, but like I said before, proof by examples are not proofs, because I could possibly find another number that doesn't work both ways. So we're going to verify that the two functions are inverses of one another by doing two function compositions. So this is what you do need to write into your notes. So you need to copy down where we verify. So let's verify starting with this, that f inverse of x, let's show that it equals x, and f of f inverse x would be f of x cubed minus 4. Replace f inverse of x into parentheses with its function, x cubed minus 4. That means I look at the f function, and wherever there's an x, I'm going to put x cubed minus 4 in its place. So I'll have the cubed root of x cubed minus 4 plus 4, and that's what I have here. And as you can see, the -4 and the +4 will cancel out, and I'm just left with the cube root of x cubed, and cubing undoes a cube root, so I'm just left with x. So yes, f of f inverse of x does equal x. Now let's check the function composition the other way, and it should also give me x. So f inverse of f of x is really f inverse of the cube root function here. So f inverse of the cube root of x plus 4. That means I look to the inverse function, and everywhere there's an x, I'm going to replace it with this function, the cubed root of x plus 4. So that will give me, in parentheses, the cubed root of x plus 4, close parentheses, cubed minus 4. Don't forget to cube what it is that you're replacing x with. Okay, and notice the cubed undoes the cubed root, so I'm just left with what's under the radical sign, x plus 4, and then I have to subtract 4. Well, the +4 and -4 cancel, and I'm just left with x. So yes, f inverse of f of x also equals x. So now I've proven that the functions are inverses of one another by doing the two function compositions. It is verified. So in conclusion to the videos, if you're asked to graph a function and its inverse, make two xy tables, swapping x and y to get the points on the inverse functions graph. And if you want to find a rule for the inverse function, step 1, replace the f of x with y, then swap x and y, and then solve for y. And remember, you can also do step 4, replace the y with f inverse of x or g of inverse of x or whatever it is. And the next thing that you want to remember is that if you have to verify that two functions are inverses of one another, you have to do two function compositions. Show that f of f inverse of x is equal to x, and also show that f inverse of f of x is equal to x. Lastly, don't forget that the horizontal line test will tell us if a function is one-to-one, and if it is one-to-one, then its inverse is a function, and we say that the inverse exists. So you have successfully made it to the end of both videos for the sequel to section 4.5, inverse functions. You're done.